Hello, this is Kuntal Chakraborty, Assistant Professor of Electrical Engineering Department, Greater Kolkata College of Engineering and Management, GIS Group. I am just going to give an important lecture on Introduction to Measuring Instruments. So before I start, I am just going to give a definition of measurement. Now, measurement, basically, it is the act or the result of a quantitative comparison between the predefined standard and an unknown quantity. Suppose we want to measure any quantity of a variable, then that will be actually compared with a standard, predefined standard. Means we have to compare a measuring quantity with a predefined standard. Now here the important part is a predefined standard. Now this term standard is applied to a piece of equipment having a known measure of physical quantity. So means whatever we are just going to measure in terms of standard, and the standard equipment should have a known measure of physical quantity. So now if you want to measure any quantity, for the meaningful results we should have requirements. The requirements are like the standard which is used for the comparison must be accurately known and commonly accepted. Now obviously that should be accurately known and commonly accepted. The standard, it may be international standard, it may be national standard, it may be secondary standard, it may be working standard. Basically, in terms of international standard, this international standard is basically agreed with the international body, and that is defined by the international committee. And basically this international standard is universally accepted. And next one is a standard which is the national standard, and this is basically the primary standard, and that is accepted by the national authority, and that is give us a standard. Similarly, we have secondary standard. Basically this secondary standard is compared with the primary standard, and this secondary type of standard is used for the the equipment for the secondary, using secondary standard that is used for the laboratory, and the working standard that we are using in the industry, and that is compared with the secondary and primary standard. So now basically this kind of standard that we have, basically that is known to us, and that is its characteristics or standard that is actually universally accepted and commonly accepted. And it has the standard body as basically similarly decide different types of units like CGS, MKS, SI units, and these units are basically accepted to everyone, and that is accurately known to everyone. So that is a primary requirement. And second one is the procedure and the apparatus employed for obtaining the comparison must be provable. Means whatever we want to measure by using any kind of apparatus and the procedure, obviously we should have to prove that that is the proper way by which we are measuring the instruments. So basically these two requirements we should have for the meaningful results. So this is the basic basic or introductory part of measurement. Now I'm just going to give the explanation of characteristics of instruments, which is very important. So instrument characteristics basically classified into two categories. One is a static characteristics, and second one is a dynamic characteristics. Static characteristics, basically the static characteristics are considered when the instrument is used to measure a quantity or a condition that do not vary with the time. Means if you want to measure any quantity of a variable that doesn't change with the time, so this kind of instruments is called the static characteristics. This kind of characteristics is called the static characteristics. And the static characteristics are like static error, accuracy, precision, reproducibility, repeatability, sensitivity, linearity, drift, dead zone, threshold, resolution, range and span. And in the next slides I will discuss all these characteristics. And next one is the dynamic characteristics. When the quantity under measurement changes rapidly with respect to time, and this kind of characteristics is called the dynamic one. So basically the characteristics that is changed with the time, that is called the dynamic characteristics. So this kind of characteristics are like speed of response, fidelity, lag, dynamic error. Now this kind of characteristics I will discuss in the next slides. So I'm just first going to discuss the static error and relative static error. This is one of the part of the static characteristics. So static error is basically the difference between the measured value and the true value. So if we see the expression, that is dA is equal to AM minus AT. Here the dA is the static error and AM is a measured value and AT is a true value. Suppose we want to measure any static error, then we need the true value of this particular instrument. So means the true value, which is very important part of the static error measurement. So now what is true value? True value is actually the average of an infinite number of measured values when the average deviation due to the various contributing factors tends to 0. Suppose we are taking an infinite numbers of reading, and if we take the average of it, if the deviation of this average it's very much tends to 0, then the value is called the true value of this particular measurements. So the static error is basically measured in terms of true value. So this is the static error. And next one is very important, that is the relative static error. Relative static error, that is the error that is basically the ratio between the relative static error or the absolute error to the true value. So here the expression ER, that is equal to dA by AT. dA is the absolute or static error, and second one at AT is a true value. So this is the relative static error. Static error and relative static error, these are the two important part of the static characteristics. And next I'm just going to discuss the accuracy and precision. Accuracy and precision. First I'm just going to discuss accuracy. Accuracy, it is a closeness with which an instrument's reading approaches the true value of the quantity being measured. Suppose we want to measure a value of a variable. If its value is approaches to closest to the true value, then its accuracy is very good. If you take an example, suppose we want to measure a value of ammeter. If its value we are just going to measure, that is a 5 ampere, and if we are getting plus minus 2% error, and by using another ammeter, if you want to measure the 5 ampere of current, then if you are getting plus minus 0.2% error, then the plus minus 2.2% 0.2% error has a highest accuracy. This instrument has a highest accuracy, higher accuracy than the previous one. So this is the accuracy, and this is the basically the closeness to the true value is called the accuracy. Next is precision, which is it is the measure of degree of agreement within a group of measurements. Means if you want to measure a value of a variable, we can take an example. Say we want to measure voltage of a particular voltmeter, and we want to measure the voltage, say 10 volt. Now if you are taking a lot of readings, and if the reading is approaches to the group actually, the readings actually belongs to 9.9 to 10.1. Now we will take the nth reading. If the value is belong to 9.9 to 10.1, then the precision of this particular instruments, that will be very good. Means we can say that the instrument is highly precise. Next I am just going to discuss a statement which is very important. That is, a precise instrument need not be accurate, but an accurate instrument should be precise. Now for this statement, we will take an example to understand the statement. Now basically we will take 2 voltmeter, that is 2 voltmeter is identical. So it is practically not possible, but theoretically we are accepting that these two instruments are identical, means same make, it has the same characteristics, same value we have for same value it's have for these two instruments. And suppose we are trying to measure a value of 5 volt by using 2 voltmeter, then obviously we will get near about a 5 volt, because this one is also the standard instruments, so its accuracy is very good. At the same time, if you take a lot of readings and its nth reading that will agree within a group of measurements, the group of measurement give us length that is that belongs to a particular, the nth value that belongs to a particular range. So that's why the instrument that will be precise. But with a voltmeter, if we connect series resistance, then the calibration of this particular instrument that will be changed. So due to that, the instrument, obviously the instrument value that will be the precise, but the instrument's reading that will be not accurate. So at that time, the instruments we are measuring, if the instruments is highly accurate, obviously like the 2 voltmeter, we are measuring the value of 5 volt and we are getting the accurate value. That's why we can say this instrument is highly precise. At the same time, if we connect a series resistance with a voltmeter, then its calibration that will be changed, and due to that obviously we will get the value in change in the second one, the instrument that is connected in series, and that's why we will not get the accurate value. But if you try to measure the instrument's value several times, then the nth value that will agree the range that we are getting a group of measurements, we are measuring we are getting from the group of measurements. So means highly precise instrument obviously need not be accurate. So means the precise instrument need not be accurate, but an accurate instrument should be precise. That is already proved, that I already discussed. So this is a very important statement. Next, that is reproducibility and repeatability. Reproducibility, it is a degree of closeness with which the same value of a variable can be measured at different time. Perfect reproducibility means instrument has no drift. Suppose we are measuring a value of a particular variable, and nowadays today I am just measuring a value of a particular variable or of a particular value, then we are getting a value. At the same time, this same value of a variable that will be measured after a week, after a month, after 3 months or 6 months. If the value remain the same, then its reproducibility is very, very good. It basically depends on time, and it's basically, if the value remains same, then the kind of instruments this kind of instruments reproducibility is very, very good. Next is the repeatability. Repeatability is the ability of an instrument to reproduce output readings, so when the same measured value is applied to it consecutively under the same conditions and in the same direction. Means if the condition remains same, and if we apply a particular input to an instrument, its output we are getting that is repetitive in nature, means the same output if we get every time, so means its repeatability is good, and it actually not depend on the time. So if we apply any kind of input, a particular input to an instrument, and every time if we get near about the same value, and then the repeatability of this particular instruments is very good. So next we are just going to discuss the topic which is the sensitivity. This is also a very important characteristics of indicating instrument. This is a static characteristics, If we apply some input, then obviously we will get some output. This is the curve. Basically the sensitivity, if we try to define it, then the ratio of infinitesimal change in output to infinitesimal change in input. Basically if we give some change in the output input, then we will obviously get some output. So if we plot this curve, then we will get this kind of curve, and if we take the slope of it, then obviously the sensitivity that can be written as dy by dx. Here the dy is actually the change in output and dx is the change in input. So for a system or a indicating instruments, the sensitivity may be highest when the sensitivity is 1, means change in input is equal to the change in output. But practically it is not possible, because obviously for a particular system or particular instruments there will be some error. Due to that we will not get exact value, but obviously we will get some change in output, but we will not get the exact value. If the sensitivity is near about to 1, so it's the instruments has a good instrument is a very good sensitive to a particular input. So this is the sensitivity, and this is very important characteristics of indicating instruments. Next is a linearity, which is very important. That ability to reproduce the input characteristics symmetrically is called the linearity. Suppose if we apply input to a particular instrument, then obviously we will get some output. But if we get the proper output, then obviously we will get the curve like ideal one, that is from the origin, that is it is generated, and it's a straight line like a curve, and we will get this ideal like curve. But due to some error occurred, or due to some problems in the system or instruments, obviously we will not get the ideal curve. Obviously we will get this kind of actual curve, and this is basically non-linear, not the linear one. But our aim to any kind of instruments, we are trying to measure any value, and that should be linear. But due to some problem or error in the system or instruments, obviously we will not get the exact ideal value like this. So obviously we will get this kind of actual value, and that is the non-linear one. And this non-linearity is due to viscous flow. It may be different reason for a particular system. If for a flow meter, if we'll try to measure the flow of a particular liquid or gas, and due to some many reasons the flow that will change, and due to that obviously due to the viscosity of a flow that will change, and due to that we will not get the exact linear curve, and we will get some change due to change in viscosity. We will obviously get some non-linear curve. Non-linear element in the measurement device. In a measurement device, if there is some non-linear element, due to that obviously we will get the non-linear output. Similarly, resistance change in the system due to temperature. Suppose resistance of a particular system changes, that will basically due to change in resistance. If it has a negative temperature coefficient or positive temperature coefficient, due to change in resistance, the temperature resistance that will obviously change. Due to that obviously we will get not the exact linear output. Obviously we will get the non-linear output. These are the reasons, and etc. We have a lot of reasons so by which we can explain this non-linear curve. So this linearity can be two type basically. One is a terminal linearity and best fit linearity. If 2 point, that is a start point and end point, is connected, and in between we have a deviation in one side, either in the left negative side or positive side, then this kind of linearity is called the terminal linearities. But best fit linearity is like this curve one, that is the actual curve is showing the best fit linearity, where some point is tends to 0, and some point we are getting in the positive one, and some points we are getting the deviation in the negative one. So this kind of arrangement is called the best fit linearity. But in case of terminal linearity, means start point and end point that will be connected, and we will get deviation throughout in the positive side or in the negative side. So this is the linearity, and this is a very important characteristics of indicating instruments. Next is a drift. It is a gradual shift of instruments indication over an extended period during which true value of a variable does not change. Basically, suppose we are measuring a value that we are providing in the input, and we are getting this kind of curve. Obviously, this is a linear one I already discussed, and there is no error. But due to some error in the instrument, obviously due to some drift, there will be some gradual shift of the instrument's reading. This one is the ideal one. If there is some drift, due to that the shift will be there, and we will get this kind of curve. So throughout this output span, we are getting a shift. So this kind of arrangement, this kind of problem we are getting in the instruments, and this kind of gradual shift is called the drift. So drift may be three types. One is a zero drift, one is a span drift, and third one is a zonal drift. Zero drift, this kind of arrangement is called the zero drift arrangement, because the span of drift in any section is the same throughout the measurements. Here, if the drift is, say, the value is 2, similarly in the output upper portion, the value that will be 2, and 2 minus 2, that will be equal to 0, means the overall drift is 0. So this kind of drift is called the zero drift, and this drift is basically is a span drift, because the span is increases throughout the measurements. Initially the span was small, and after the measurement goes on, the span that is increasing. So this is basically the span is increases. This one is the ideal curve, and this one is the actual curve. So throughout the measurement the span is increasing. That's why this kind of drift we are getting in a span manner. So that's why this kind of measurement is called drift is called the span drift. Next one is a zonal drift. When the drift occur over a span of an instruments, particular section we will get a span drift, a particular section we are getting the zonal drift, zero drift. So this kind of arrangement is called the zonal drift. It depends on the zone on which we are getting a span or the zero drift. So these are the drift, and which is very important. Next one is a dead zone, the largest change of input quantity for which there is no output of the instrument. Suppose we want to get some value in the output due to change in input, but due to some input change we are not getting any output. So this kind of region is called a dead zone. So here we are seeing that we are giving some input, but we are not getting output from this section. So this zone is called the dead zone, and this time in which no output are getting due to change in input, this time is also called the dead time. So this is a very important one. We are applying some input, a particular input, due to some extent we are not getting the output. So this region is called the dead zone of these particular instruments, and this time that we are not getting any output, this is called the dead time. This is next one is a hysteresis. Hysteresis, we already know the BH curve of electromagnetism, we already know. But in case of indicating instruments, if we taking some reading in a loading manner, suppose we in the increasing manner, suppose we are taking a value of a voltmeter from starting from 0 to 20 volt, and say 0, 2, 4 and 6, like in this way up to 20. Similarly in the unloading manner, then we will not get the output as same one. There will be some deviation, and due to that this kind of BH loop type curve we will get. So this kind of arrangement is called the hysteresis of a particular instruments, means the loading and unloading curve will not be the same due to some error of the instruments, and we will get like a BH loop of our electromagnetic system. So that's why our magnetic system. So that's why we will, this kind of arrangement is called the hysteresis. As the curve is looking like hysteresis curve, so that's why it is called the hysteresis. Next is a threshold, which is very important one. If the instrument's input is increased very gradually from 0, there will be some minimum value below which no output change detected. This minimum value is defined as a threshold. Suppose we are increasing our value, then suppose we will not get any output for a particular gradually we are changing from 0 to a particular value. After that some minimum value we are providing, after that we are getting a output. So this kind of minimum value that we have to provide to get some output, so this kind of value is called the threshold of this particular instrument. So if the instrument's input is increased very gradually from 0, there will be some minimum value below which no output change detected, and after that we obviously we will get some output. So this particular value is called the threshold of this particular instruments. Next is the resolution and range and span. Resolution of an instrument, it is the smallest increment of the quantity being measured which can be detected by an instrument. Means the smallest increment that can be detected by an instrument, which is called the resolution of this particular instrument. Suppose we want to measure a voltage by using a voltmeter, and we can measure 0.1 volt. So this 0.1 volt basically is called the resolution of this particular instruments. And next one is a very important thing, that is the range and span. And if X is the lowest point of calibration and Y is the highest point of calibration of a scale of an instrument, then the range will be from X to Y and span will be Y minus X. So the range is a starting value that is from X to Y, that is the range, and the span will be Y minus X, that is will be the span. And now we will going to discuss the dynamic characteristics. Dynamic characteristics I already discussed. Basically, if the characteristics is changed with the time, so this kind of characteristics we will call the dynamic characteristics. First, we are just going to discuss, that is the speed of response. It is the rapidity with which an instrument's response to changes in measured quantity. Suppose we want to measure a value of a variable that is we are applying into the input, and that is changing with the time. So at the same time the output will change, and basically what amount of what is the response, how fast it is respond, this depends on the instrument, whether this change in input responded very fast or not. If it is responded fast, then this kind of instruments speed of response is very good. So means it is the rapidity with which the instruments responds to change in measured quantity. So we are applying some input, and due to change in input, how fast the output changes response. So this kind of characteristics is called speed of response. Next is the fidelity, that is ability of the system to reproduce the output in the same form as the input. Suppose we are giving some input that is changing with the time, say a sinusoidal like curve to our input device, and if we get the output the same replica of the input one, means a sinusoidal curve, then its fidelity is very good. Means the ability to reproduce the same value that we are applying in the input, so we are getting the output as a replica of the that is applied in the input. So that's why the system that we'll call a good fidelity system. So this is the fidelity, and this is a very good dynamic characteristics, obviously that is changing with the time. Next is the lag. It is a retardation or delay in response of an instrument to changes is in measured quantity. Means if we are applying some input, after some delay there will be some output. So it will take some time to respond into the output changes. So this delay or retardation is called the lag. In between this lag we will not get any changes into the output. So this retardation or delay is called the lag. This is also a dynamic characteristics. Next is a dynamic error. It is the difference between the true value of the quantity changing with the time and the value indicated by the instrument system if no static error is assumed. If there is no static error and we are giving some input that is changing in time, and due to that obviously we will get some output that is also changing. So if there is some error, then this kind of error is called dynamic error. But one thing is important for these characteristics, it should not have any static error. So this is the dynamic characteristics of an indicating instruments, and this is a very important characteristics of indicating instruments. So for a particular instruments, if an instrument that will be very good if there is no static error, but due to some error obviously we will get some static error, and it should not have accuracy, and obviously the accurate instruments reading that should be very close to true value, but due to some error obviously we will not get exactly true value. So we will try to manufacture a device whose accuracy is very good, near about to true value. And obviously if accuracy of a particular instrument is very good, then the instrument obviously that will be very highly precise. And I already discussed the reproducibility of a particular instrument. Instruments should have a good reproducibility, because every time we are using, say instruments are using now or 1 week later or 6 months later, so the value it is reproducing that should be equal or near about to equals, then the instrument's reproducibility that will be good. Next, the repeatability of an instrument that should also be good. Every time we are measuring the instrument's reading for a particular reading, and every time if we get this output as the same one, so its repeatability is good, means repeating the same value, but it doesn't depend on the time. So the instrument should have this kind of characteristics. If we try to manufacture any instrument, so these two characteristics, reproducibility and repeatability is very important. Next, sensitivity. Instrument sensitivity should be high, and linearity, we obviously try to reduce non-linearity so that we can get the linear curve. And instruments should not have any drift, because some error or due to age of the instruments we are getting some drift. So that's why it should not happen into instruments. So instruments should not have any drift. And dead zone, if the instruments don't have any instrumental error or manufacturing defect, so it shouldn't have any dead zone. But obviously there will be some problem due to that. Obviously there will be some dead zone, and threshold will be there, because to operate the indicating instruments we need some force to operate or to deflect the pointer. So we need some minimum amount of force, and that's why there will be some threshold, and we have to minimize that. And resolution, obviously for a particular instruments, the smallest increment that can be measured, the reading means we can measure the smallest value of a particular variable, a resolution of a particular instrument that should be very good, so that we can measure the very small value of a particular instruments. And range and span, that is for a particular instruments, that is not depend, basically it doesn't matter. Range, obviously if the range is very good, say the scale is showing from 0 to 300 volt, and the scale that we are getting 0 to 200 volt, obviously 0 to 300 volt, that span from 0 to 300. So this the scale that will give us the maximum measuring value. So obviously the span and range, that should be high for a particular instrument, and the speed of response, that should be good for a particular instruments, so that the response may be faster. And fidelity, obviously we need a fidelity, good fidelity of a particular instrument, so that the replica of the input that can be get from in the output. And there shouldn't be any lag, but due to some error of the instrument, obviously there will be some lag to response in the output due to change in input. So we will get some lag. So dynamic error, any error of an instrument, it may be static or dynamic, that is not required for an instrument, for a good instrument. So we will try to neglect, or we will try to eliminate the error, it may be static or dynamic error. So that is the static and dynamic characteristics of an indicating instruments. And thank you all. Thank you.